Find the area of the region bounded by the curves f of x and g of x. We're going to graph this first because if we look at the graph and see what's happening, we're going to find out something interesting is going to happen with the area between these two curves. So if you had a calculator, this would be easy to solve. If you had a non-calculator, it would be harder to solve. So we're going to look at both of those. How would you do this without a calculator? How would you do this with a calculator? So first of all, to get a sense of what's going on, we're quickly going to sketch both of these. So those skills that you developed in grade 12 for sketching graphs are going to come in here. We're not going to do the whole sketch via the derivative and finding your critical points and find increasing and decreasing. We just see x cubed plus 2x squared. We know that that's a cubic function. It's a positive cubic function, so its end behavior will act like a line. It'll start in your bottom left corner and end in your top right-hand corner. You can factor this easily. So f of x is equal to, take out an x squared, and you get x squared, x plus 2. So what do we know about f of x, which I will do in blue? We know that there is an x-intercept at 0. And we know that there is another x-intercept at minus 2. Now, if the graph has to start from down here, it's going to go through negative 2. What do you know when it hits this 0? What's going to happen? It is going to bounce off of that one because it has a multiplicity of 2. So if you remember that from last year, you can sketch this quickly. So there's our graph of our blue graph. I'm going to graph g of x in green. You can factor g of x as well. There's a common factor of x that you could take out, leaving you with x plus 2. And again, it would have 0 and negative 2 as its x-intercepts. And we would have our parabola look like this. Now I should probably, I am going to fix this part up of both of these graphs. An x cubed graph will go up quickly. A parabola will go up slower. So this is kind of an idea of what this looks like. A little bit unsure of what's going on right here. We can see from our graph the way that we solved our x-intercepts that we're going to get a value at negative 2 and 0 that are the same. But there's a possibility that there might be a third point where these two graphs intersect, depending on how I've drawn it. Maybe I've drawn it wrong, but it looks like there's that possibility. If we want to find the intersection points, we would have to set f of x equal to g of x. So if I did that, I would have x cubed plus 2x squared equal to x squared plus 2x. How we would solve this is we would set it equal to 0. So move the x squared and the 2x over. You could factor out a common factor of x. And then this factors nicely 2x plus 2, x minus 1. So that does tell us that there are 3 solutions here. When x equals 0, that was one of our x-intercepts. When x equals negative 2, that was another of our x-intercepts of both graphs. But we now know that they intersect, that red point, at x equals 1. If we wanted to, we could go back to our graph and say, I know this point happens at 1, 3. Because I could plug 1 either into g of x and figure out that it's 1, 3, or I could plug 1 into f of x and figure out that it's 1, 3. So what makes this question different is that when we want to find the area between the curves, I could color, this would be one area between the curves. Okay. And this would be, let's see, I choose another, we'll go orange. This would be another area in between the two curves. So we got that purple area and that orange area between those two curves. What's the difference between both of those areas? Can you see in the purple area, our blue graph is the graph that's on top. Whereas in our orange area, the green graph is the graph that's on top. And we noticed earlier that if we were figuring out the area between the curves and you put the wrong graph on top, you got a negative area instead of a positive area. So in this case, if we just tried to find the integral from -2 to 1, one of these areas would be positive and one of them would be negative, depending on which one you put on top. So in order to figure out the exact area, the purple area plus the orange area together, you're going to have to set up your integral into two parts. One part is going to be the blue graph on top minus the green one, and the other part will be the green graph on top minus the blue one. So we'll color code this so we can see what's happening. So our first integral goes from -2 to 0. From -2 to 0, that's where we saw the blue graph was on top and the green graph was on the bottom. So I would write my blue graph, which was x cubed plus 2x squared, minus my green graph, which was x squared plus 2x. I'm going to run out of room. I'm going to move this over, shrink it a little. There we go. This dx, all of this dx, will give me that purple part. Then we're going to need to add to that the integral from 0 to 1. And this time, our green graph was on top minus our blue graph. And that part, that would give us our area of our orange part of our graph. Okay, see what we've done so far. We drew our sketch. We noticed that there was an area between the curves, but it came in two different sections, that purple section and that orange section. We set our equations equal to each other so we could find all of our intersection points, even though when we sketched we were able to see two of them right away because we used our x-intercepts to help us sketch our graph, and they happen to have the exact same x-intercepts. When we solved that, we found out that x equals 1 was the third intersection point, so we labeled that point in red. Now to find the area between those two curves, the purple section was the blue graph on top minus the green one underneath. So we color-coded that, so we had the blue one minus the green one. And then for the orange part, the green graph was now on top, so we did the green graph minus the blue graph. When you simplify both of those, and before you integrate, you will want to simplify both of these. You will get here x cubed plus x squared minus 2x dx. And here you're going to get negative x cubed minus x squared plus 2x dx. So all that, once they're simplified, all you see is that one is a negative of the other one. So now when we integrate, and in our purple section, which we should do in purple, we would have something minus something. Oh, I should integrate first. Sorry, got a little ahead of myself. When we integrate, we're going to get x to the 4 over 4 plus x cubed over 3 minus x squared from negative 2 to 0. Plus, and for our orange part, I don't know if it makes sense to use orange. Can you even see this? From 0 to 1. Purple part. Plug in 0. Whew. That feels good. Plug in negative 2. And then for our orange graph, plug in 1. Plug in 0. And now we're going to just simplify to find out what the final answer is. So, what do we have in our purple part? We're going to have 4 minus 4, a negative 8/3 times a negative. That will just be 8/3. And then our orange part, negative 1/4 minus 1/3, that'll be 3/12, negative 7/12 plus 1 plus 5/12. Get a common denominator here, 32 over 12 plus 5 over 12. Three and 1/12 is what we've got, pending any mental math errors or anything like that. Now we're going to try it with our calculator to see how does being able to use our calculator in this question. Obviously, it's going to make things easier. We're going to graph both of these graphs. So on my calculator, I'll go to y equals, and in 1, I'm going to have x cubed plus 2x squared. And in my other graph, I'll have x squared plus 2x. We're going to go zoom 6 to a standard window just to see what it looks like to begin with. So there's our cubic graph. There's our parabola. Now, as far as what we're wanting to see, we're wanting to see the area in between the two curves. So as far as my window goes, can you see that if I would change it from negative 4 to 3 on my x-axis, and negative 1 to 4 on my y-axis, I'll be able to see this more in depth. Ooh, I might have to go a little bit lower. Let's see. Oh, that's close. So now we want to find the area in between those two curves. So what we did when we integrated, and I'm going to show you something that's kind of neat in your equation. Instead of having to retype them, if I wanted to find the areas, like the first one, we did the blue graph minus the red graph. So if I want to do that quickly in my calculator, I can just type in y2 minus y1. How do you type in y2 minus y1 quickly? You can go either the fastest way is go second y equals, go over until y vars, and you can say, I want to take the blue one, y1, minus, and then I want to take y1 minus y2. Now, if I graph this right now, there's going to be a lot of things on my graph. Instead of having them all graph, I can go to these equal signs and I can push enter on the equal signs, and what it will do is just graph the one that's highlighted. So now it's just going to graph the black one, and the black one was my blue graph minus my red graph. If I want to find the area under that curve, I can go to number 7. I can say, let's start at -2, and let's go to 0. And this value, 2.667, according to what we calculated before, that should have matched up with this 8/3. If you change 8/3 to a decimal, you get 2.667. So it appears that our mental math has worked out nicely for that section. How did I get that y2 minus y1? I'm going to do that again, because for the second part, we're going to want to do y2 minus y1. So to type in y2, do you have this option? Does this come up? If you go alpha y equals. And then you can go over either with your arrow keys, or you might have to push the thing under y variables. Now I'm going to do y2 minus alpha y equals, and then y1. So for my purple graph, now I'm going to do y2 minus y1. Because that would be our green graph minus our blue graph, which was the orange part that we shaded before. Okay. Anybody not have that option? Because if you don't have that option and are still looking to type in y2 minus y1, you can do it by hitting variables and then going over to y variables, clicking enter on function, and then they all appear. So there is another way of finding these if you don't have them that first way. I'm going to go back to y equals. Now I'm just going to look at this purple one. Well, I'm actually going to look at both. Let's hit graph, because there's my black graph with the part that I shaded. Here's my purple graph. What do we notice about our purple graph? It's just the reflection of the other one, because it's just like multiplying by a negative. So this area that I want to find on my purple one is going to go from 0 to 1. So I'm going to go second, calculate number 7. And number 7, when I do it, will pick one of your functions. Do we want the black one? No. So if you toggle with your arrow keys, it'll switch, and now I'm on the purple one. I want to find it from 0 to 1, and it calculates that area of that purple one. It's telling me it's 0.416. Quick check on another calculator here. Is 5/12 0.416? It is. Happiness all around, because we made no mental math mistakes in our first question. Taking those two, how do I add those together? I should have done something. I mean, you could have written down that first answer, right? The 8/3 I should have written down the decimal, and then I could write down the 0.416. The interesting thing is, whenever you calculate something on your calculator, if you go quit at this point, it temporarily, like for 2 calculations, will store it as x. So right now, if I push x, no, it didn't store it. Never mind. Sometimes it does. Did it store the answer that way? Not anymore. I'm going to try that again with the answer button. I'm not very confident right now in that, but we're going to try that again. I'm going to go, let's say I'm calculate this. I'm on my purple function from 0 to 1. It reshades it in for me, figures this out. I'm going to see if I go second answer. Yes. It remembered that the last thing I calculated was that 0.416. I'm going to call that area B, so I'm going to store this as B, just to have that as an answer. Fancy. I'm going to go back and calculate the integral from -2 to 0 again on the black one. Get the 2.667. I'm going to store that answer as A. Oh. Uh-oh. This could be bad luck right now. Yes, it worked. So then if I want to add those 2 areas together, I can just go A plus B. And I get 3.08. Math, change that to a fraction, and it is 37 out of 12, like we found without our calculator. But there's a lot of cool calculator buttons that we pushed on the way, which is a little bit confusing. Couple of things. If you had wanted to, you notice how we had typed in y1 minus y2, and then I retyped in y2 minus y1. Let's say I just did the black one. So I'm going to regraph this with just the black one. If you just had the black one, you could have found your area between -2 and 0. I'm not going to do that again because we've done that 3 times. But you could also calculate the area of your black one from 0 to 1. And that's going to give you 5/12, but negative. So if you wanted to, you could just use this one as long as you remember, oh, I have to make this positive. Do you want to be creative? A little bit? Can you see that when you find this, it'll have one area positive and one area negative? How could we do this all together with our calculator in one fell swoop? What's that? So if we absolute value it, so let's go to y equals, let's go here and insert an absolute value. Absolute values under math, hit the math button, over 1 to number, push enter, O. I guess I still have to retype in the y1 minus y2. So if you had put absolute values, now when you graph it, bonk, bonk, bonk. And now you could calculate the whole area, number 7, all the way from -2 up to +1. Nice. And you get the 3.08, which is the 37 over 12 anyways.